Hello, so to get started, what I want you to do is I want you to answer the question, what does a year measure? So does a year measure how long it takes for the Earth to go around the sun once? Does it measure how long it takes for the Earth to spin around its axis once? Does it measure how long it takes for the moon to go around the Earth? Or does it measure how long it takes for the sun to go around the Milky Way once? Maybe this question's too easy. I think this question might be too easy. Yeah, I think this question is pretty easy. Is too easy. Maybe I need. Do I have time to come up with a harder one? I don't know. Um, uh, um, oh, I can't think of a harder one. But for now, yes. I think so. I think that the general trend is I'm very pleased with the quality of your elementary school education. Clearly, at one point, your teacher definitely taught you something. That's good. That's good. I would have been very concerned if you didn't know how long a year was. Yo, what up? What's up, Miguel? Um, what is up? Laugh at me. I'm very insecure. I'm very insecure. Okay, I'm very insecure. I can't acknowledge it. Okay, yeah, yeah. Fake it till you make it. Yeah, 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 yeah. No, I'm super confident. Yeah, yeah. Wow, everyone has gotten this right so far. This question is way too easy. But I guess that's good. That's good. It's good that you guys actually learned something at one point in your lives. Um, okay, we'll take another minute or so just because this is pretty easy. So yeah, I guess I was kind of expecting like this to be more of a spread of answers, but I don't know. I don't remember. I don't remember when I learned this. I just remember that I learned this at some point, and I never forgot it. Okay. Well, okay. Do we know how long? Do we know how long it takes for the? Um. No. Actually, no. I think that's probably too easy too. Just forget it. Okay. So I'm glad that all of you know how long what a year measures. That's very good. That's very good. Um, so the reason why we're talking about years is because we are talking quite a bit about revolutions because orbital motion is literally planets orbiting around the sun, revolving around the sun, and so the year is one unit of measurement we use to measure that. What I want you to think about is basically this, right? So a year is how long it takes for the Earth to go around the sun, 365.24 days. Nothing new, I think. But the thing is, right, that's not the only thing that we can measure the revolution time of. We can also measure how long it takes for a clock to complete a revolution. Oh, you also can't even see. You can't even see the slides. That's, uh, what'd you say? Oh, that's for the open house. Yeah, 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 that's yeah, yeah, yeah. Uh, where is this agenda? Okay, here we go. Okay, so yeah, so how long does the revolution take? It takes 365.24 days. Um, the thing is, we can also measure how long it takes for a clock to go around to complete a revolution. We can also measure how long it takes for a merry-go-round to complete a revolution, right? We can measure the revolution time of anything, pretty much. What are some other things we can measure the revolution time of? Like, oh, if you know what like an RPM is, RPM literally measures revolutions per minute. That's something you usually use to like measure stuff in cars. And it's basically like how much the engine is sort of going per minute. So there's a lot of different ways you can measure revolutions. What I want you to think about is how do you measure the revolution time of an object? So um, I think I phrased this wrong. Um, no, yeah, I think I phrased this wrong. Okay. What I was trying to say is basically this. Okay, so um, basically to measure how long it takes to revolve around an object, you're basically sort of measuring how long it takes to travel a certain distance at a certain. So one thing you can do to measure how long it takes to revolve for an object to revolve is you sort of pick one point and then you wait for the object to go around. And then when it gets back to the same point, you say, okay, that's how long it took. That's how long it took. That's the time of the revolution. That's what we call the period of revolution, basically how long it takes to complete a circle, a revolution. And what we can also do is we can also say the object is traveling at a certain speed, and we wanted to travel a certain distance. And so we take the amount of distance we take, we take the amount of distance we're trying to cover, and we divide it by the amount of speed. We can also look at how much time it takes. So that's sort of how we might measure the time it takes to travel a certain distance in terms of a linear, like if it's a linear line. But we can also do the same thing for a circle. Basically, the idea is that a circle is essentially a straight line that's just curved. Basically, there's nothing different about a circle versus a line versus a straight line. It's just that you just bent the line in the shape of a circle, essentially. Right? You can still do the same thing, right? So if I want to measure how long it takes to go in the circle, I can still take the amount of distance it takes to go around the circle, and I can divide it by my speed to figure out how much time it takes. So if I have a, if I have a if I know my circle has a total length of a total circumference of this, and I divide it by my speed, I can then figure out how long it took to travel to travel around that circle. The idea is the same, right? There's not a whole lot of difference between measuring how long it takes to go a certain distance in terms of a linear line and how much it takes to travel that distance in a curved line. So because the thing is, right, the general principle is the same. If I can figure out how long it takes to go, if I can figure out how much distance how much distance it takes to go around the circle, and if I can figure out how fast I'm going around the circle, I can then figure out my time, right? So what I want you to do is I want you to quickly give you a couple minutes in your groups, and I want you to figure out how can you measure the distance around a circle, which would be a little bit easier. And then how can you measure the speed around the circle, which actually is quite a bit harder. But I'm gonna give you a couple minutes just to see if you can figure out how you can measure the distance around a circle and how you can measure the speed around a circle. Because if we can take our distance and if we divide it by our speed, right, we can then figure out how long it takes to go around that circle. Yeah, so how do you find the distance around a circle, and how do you find the speed around a circle? So in your group, see, yeah, like in terms of like
My bad, Mr. Who.
How's it going, Jojo?
Good.
Okay, so in terms of measuring the distance around a circle, I think most of you have sort of figured this one out, right? To measure the distance, we can just use the circumference formula, right? That if we know the radius of the circle, what we know is that the radius of the circle, if you multiply it by 2 pi r, right, this will give us the circumference. So, and that tells us the distance around a circle, which I think is not too complicated. But what's much harder though is figuring out how you can measure the speed around a circle. And this is where we need to use something called, the thing is, if we use a regular speed, that only tells us how fast we're going in a straight line. If we want to figure out our speed around a circle, we're going to do something else. We need to actually do something else called an angular velocity. So our angular velocity basically tells us how fast we are going around a circle per second. It's basically our rotation speed. The idea is you can consider if the circle has a length of yeah, so we use something called the angular velocity, which is just basically our rotation speed. It basically measures how fast you're going around a circle. So to calculate this, we use something called omega, which is like it looks like a W, and you can calculate omega just by taking the velocity and you divide it by the radius. In terms of like where omega comes from, which you could, if I were to sort of, I guess, quickly derive it for you, I think that might actually make more sense. So basically, like if I were to try to figure out how long it takes to go around a circle, what I might do is this: I might take the distance around a circle, which is 2 times pi times r, and if I figure out how fast my linear velocity is, which is v, right, I can get my time. Basically, if I know how long it takes if I know how long the line is, and if I know how fast I'm going in a straight line, I can then figure out the time it takes. Well, what if I want to work, what if I don't want to work with how fast I'm going in a straight line, but actually how fast I'm revolving? This is where we convert this risk in terms of, this is where we turn this, the v over r, this is where we turn this into 2 pi over omega. So basically it's saying, if I'm trying to go around a circle, which is 2 pi, if I divide this by my rotation speed, omega, I should get my time, t. So this is where the omega comes from. It's literally just taking v velocity and dividing by a radius, and that'll give you something called an angular velocity, or basically it's rotation speed. And we use the symbol omega to find that. So this is pretty important because when you deal with rotations, you stop working with linear quantities such as velocity, and you start working with angular ones. Sorry, it's like circular ones, which is omega. So, but the idea is the same, right? If I take the distance around a circle and I divide it by my velocity, I should get my time. And in this case, because we're working in a circle, we're now going to use our angular velocity. So what we want to do now is we want to figure out the period of revolution. So basically, what I mean by period of a revolution is it basically means how long does it take to go around a circle once. So for example, the Earth takes the Earth 1 minute, 1 year to go around the circle once. So we can say that the Earth has an orbital period of 1 year. The minute hand on a clock takes 60 seconds to go around the clock once. So you could say that the minute hand has an orbital period of 60 seconds. So the period is just how long it takes to go around a circle once, essentially. So in terms of how would you calculate the period of rotation in general for a circle, this is where we just use our general idea, which is if I know how
if I can figure out my my angular velocity, if I know my angular velocity, if I know my radius, if I know my if I'm trying to figure out the time, what I can do is I can do this. I can take my my circle. So if circle is the length of a circle is 2 pi radians, and if you divide it by omega, so basically it's basically saying the length of a circle 2 pi dividing by omega, the angular velocity. This will give us the time it takes to go in a circle. So 2 pi over omega should equal time. Where this t means the period of rotation. Yeah, so we're going to use this concept of period it's a very important concept in terms of orbital motion because it basically tells us how long it takes to go around something once. And so when we're working with planets, we want to know how long it does it take for a planet to go around the sun once, essentially. This is where you use the period. What you use the word, and in order to find the period, we're going to need to use the angular velocity, which is omega. And once again, omega you can get from the linear velocity and the radius itself. Okay, so right, to figure out the period, what we can do is we can say a period of something is so to calculate the period, I think, did I mess this up? I think I'm, oh yeah, so I think I wrote this wrong. This is actually, what this should say is 2 pi r over b. Okay. Okay, here we go. Okay. So to calculate the period of revolution, we can use this formula here. This should say rough day for me. Okay, so this should say 2 pi divided by w divided by omega. So basically, to find the period of a revolution, what we can do is we can take the period. The period is 2 pi r divided by the velocity, which is the same thing as 2 pi divided by omega, which is what we did previously. So basically, the formula is basically time is equal to distance over speed. So to calculate the period, we can use 2 pi over omega, or we can use 2 pi times r over v. I mean, so you're going to need to use this later on to convert some velocities into times, essentially. So you're going to need to be able to know how to use this. Because what's going to end up happening is we're going to have an expression for the velocity of an object, and we're going to want to convert that into an expression for the period of an object. And so in order to do this, you need to be able to figure out how do I convert a linear velocity to a time. And this is what you do here. If I know the circumference of a circle and I can divide it by my linear velocity, I will get the period. You can also use the angular velocity here. That's also okay. But yeah, so that's basically the general idea. Yeah. Okay. So one of the ways that we can sort of look at orbital motion is we want to look at how much time an object can cover in how much area essentially an object can cover in a certain amount of time. So one of the main important concepts in orbital motion is that basically, if I were to look at an ellipse and if I were a planet going around the ellipse, I can cover a certain amount. The amount of area I can cover in a certain amount of time is going to be the same anywhere across the ellipse. So for example, if it takes me 1 month to go from, if it takes me 1 month to go from, I'm not even sure, where do my slides go? Yeah, here we go. Okay, so if it takes me 1 month to go from here to here, this the amount of area here is going to be the same as this. So if it takes me 1 month to go from here to here, the amount of area covered here will be the same as the amount of area covered here, as long as the amount of time is the same. So as you can tell here, right, this triangle here is a little bit wider, but it has like a shorter height. This triangle here has a longer height, but it has a smaller width. So the areas are the same as long as the amount of time you took for the planet to cover that time is the same. I don't know if this makes any sense. So basically, like if it takes me a month to go somewhere, the amount of area covered in that ellipse is going to be the same wherever it goes. So this is really important because we're going to use this to basically look at how the velocity of a planet changes as it's going around the sun or is going around a star. To give you an idea of what the simulation might look like, a simulation of what this might look like. So this is a simulation for the for what this Kepler second law might look like in terms of an actual planet. So if I were to run the simulation here, so this is basically how much area this covered in a certain amount of time. This area is going to be the same as this area. This area is going to be the same as that area. All these areas are going to be the same. So, and as you can tell that when the planet gets farther away from the sun, the orbital distance gets longer, but the base of the ellipse, of the area covered, is sort of smaller. But it ends up being that that no matter what happens, the amount of area covered total is the same. So we'll use this to basically figure out how to sort of make predictions on how fast the planet is going around the sun at these very different locations, because this has to hold true. The amount of area that the planet has to go around the sun has to always stay the same, as long as you're covering the same amount of time. And so we're going to use this to figure out how fast the planet goes at certain points in its rotation. This is kind of like hard to explain. It's sort of like, yeah, I guess that's, honestly, that's the only thing I can really think about explaining it. It's basically, yeah, as it goes around this, so it has an elliptical orbit. As it goes around the elliptical orbit, if it takes 1 month to go a certain amount of area, that amount of area is going to be the same as any other area that takes 1 month. So the key thing here is that the amount of time has to be the same. So if it takes me 2 months to go one area, it takes me 1 month to go another area, the two areas will not be the same. The time intervals have to be the same in order for this to work. But this is true regardless of what happens. That's why it's called a law. It's very, 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 it's like it's factual, I guess. So that's what we call Kepler's second law. He has another law here that we call the third law of planetary motion. And this sort of relates the orbital period of a revolution to the semi-major axis. So this is what we talked about previously when we talked about the period of revolution. So the Kepler's second third law states that the period of revolution of a planet is proportional to its semi-major axis cubed. So the semi-major axis is basically because a planet is an ellipse, it's basically how far the distance. It's basically the distance from the center of the ellipse to the long side of the ellipse. So that it's basically like essentially how far the planet is from the sun. You can consider it like an orbital radius, but that distance cubed is proportional to the period of revolution. So how long it takes for the planet to go around the sun once, that squared is proportional to the cube of the semi-major axis. So this is a very important relationship because we can use this to predict what the period of revolution will be as the semi-major axis changes. So what I want you to do is I'm going to put you in your groups here, and I want you to try to make a couple of predictions. Before we get into mathematical ones, I just want you to make some general ideas here. So how would the orbital period change in general as you get farther away from the sun? how does the orbital period change as we get closer to the sun? So that's one thing I want you to talk about in your group. Another thing I want you to talk about is how would the if the orbital period it takes to revolve around the sun is increasing, how would the orbital radius change? And what if the orbital period was decreasing? How would the orbital radius change? So in your group, Steve can come up with relationships between the orbital period of the object and the orbital radius, and talk about how do these change if what the other one is changing. Okay, so Okay, so I think most people sort of understood the relationship here. But yeah, the general idea is that as we get, because it's a t squared proportional to r cubed relationship, basically as we get farther away from the sun, as our radius increases, the amount of time it takes for us to go around the sun also increases. And if we're getting closer to the sun, so if our radius is decreasing, the amount of time it takes for us to go around the sun is also going to decrease. So basically, it's sort of like it's not a one-to-one relationship because it's a t squared to r cubed relationship. But the idea is if one increases, the other one's also increasing. If the other one's decreasing, the other one is also decreasing. So that's just sort of the general relationships between these. What we're going to do now is we are going to try to look at specifically what happens if one changes and if one quantity is changing. To do this, we need to first introduce the unit of measurement that we use in astronomy. So in astronomy, there are lots of units we use to measure stuff because using meters to measure stuff in space is not very effective, especially when every single distance in space is either millions or billions or trillions of meters away. So so meters themselves are not very effective. So that means we need to introduce a new unit to measure distances in space. So there actually are multiple units. There are parsecs, light years, and for right now we're going to use AU. So AU is generally the distances you use to the measuring units you use to measure stuff within a solar system. The word AU, the acronym AU stands for astronomical unit. Basically, what we calibrated AUs in terms of the distance the Earth is from the sun. So the Earth is exactly 1 AU from the sun, and we said that was 1 AU. So everything else is measured relative to that. So when we measure the distance of Mars relative to the sun, Mars is 1.52 AU from the sun, which means that the Mars is 1.52 times farther away from the sun compared to the Earth. Now, similarly, Venus is only 0.72 AU away from the sun, which means that Venus is 0.7 times closer to the sun compared to the Earth. So basically, Mars is farther away from Earth because it's 1.5 AU. Venus is closer to Earth because it's closer than the Earth because it's 0.7 AU. So that's sort of what we use to measure distances from the sun. So what I want you to do now is I want you to first what I'm going to do is I'm first going to show you how what I mean in terms of figuring out how long it takes to roll around the sun if we're looking at different distances. So here what we have in the question here, if a planet is 2 times farther away from the sun compared to Earth, how long would it take to revolve around the sun? So if a planet is 2 times farther away from the sun compared to the Earth, how long would it take to revolve around the sun? So in order to do this, we're going to need to use this relationship, Kepler's third law, which is we're going to need to use the Kepler's third law, which is the relationship that the period of revolution is proportional to the radius cubed, the orbital distance cubed, essentially. So basically, the Earth revolves in 1 year, and it has a radius of 1 AU. So basically, what we need to do is we need to take this new planet. We need to take that radius and we need to compare it to the Earth's radius. We're going to cube that, and then we're going to raise this to the period squared. So basically, the other planet divided by the Earth. We're basically looking at the radius of the other planet, and we're comparing this to the radius of the Earth. And we're comparing this to the period of revolution for the other planet. Okay. So basically, this is what the t squared portion of the r cubed relationship means. It basically the ratio between the planet's rotation and Earth's rotation of revolution is going to correspond with the period squared. So to show you what I mean by this is basically the other planet has a rotational distance, a revolutionary distance, orbital distance of 2 times greater than Earth. So it's basically 2 AU divided by 1 AU. And what we do is we're going to cube this, and this is going to be proportional to this period's squared. So when we do this, what we get is that the period of revolution for the other planet, this squared should be 8 essentially. So if we square both sides, what we get is that the other planet should have a period that is corresponding to square root of 8 times the other one. Since Earth takes 1 year to revolve, this means that this should take roughly square root of 8 times 1 year. So this is like roughly 2.something years. Oh, okay. Oh, I did not expect that. Okay. So, okay. So, so basically, what we need to do is there was a relationship between the period of revolution compared to the orbital radius. So basically, how far it is from the sun. This relation follows a t squared compared to an r cubed relationship. It's not a one-to-one relationship. It's not one-to-one. So basically, a one-to-one would be if my radius doubles, my amount of period time it takes to revolve is none. This is like a one-to-one relationship. However, this is not true. It's actually following an r cubed t squared relationship, which basically means we need to look at the ratios between these, and then we need to cube them and compare that to the ratios of the orbital period. So basically, what I said is okay, the planet's orbital radius compared to Earth is 2 times. Basically, it's 2 times bigger compared to Earth. I need to figure out how many times bigger is my orbital period going to be. So basically, since the other planet revolves at 2 AU, Earth revolves at 1 AU, this should actually be 2 times bigger. And this should correspond to how many times bigger my orbital period is. So orbital period is squared. So when I take 2 cubed, I get 8. And so my orbital period should be this many times bigger compared to this squared. And I said my orbital period should be 2.7 years. I think I'm going to need to do another example. Okay, so let's say instead of something that is 1 AU away, let's say we're looking at a planet that is 3 AU away. So this planet is 3 AUs away from the sun. Earth is only 1 AU compared to the sun. So what I want to do is I want to compare the ratios of these, and I can use that to then determine the ratio of the periods. So the ratio of the radiuses should follow this relationship, where the radius of the planet divided by the radius of the Earth, this cube should correspond to the squared relationship between the 2 orbital periods. So if I cube this, what I get is that this should equal 27. And so the amount of time, so the orbital period squared should correspond to 27. And so this would be the square root of 27 years. Okay, so yeah, it's kind of hard for me to explain because it's a proportionality thing. It's not really an equation. I mean, it's an equation, but it's like a proportionality thing. And it's not a one-to-one proportionality. You have to sort of look at the ratios between things. I think we're gonna do some practice because me just explaining it, as you can tell, I'm not great at explaining this. I think it'll be better if we get some practice in first. So what we're gonna do is we're gonna do some practice problems in terms of that. Okay, so The first practice, so these are the two practice problems. So Jupiter is, I think let's do these one at a time. So basically the general idea is the same, but Jupiter is 5.2 AUs away from the sun. So what would Jupiter's orbital period be? So we're gonna compare everything to Earth. So Jupiter is 5.2 AUs away from the sun. So what would Jupiter's orbital period be? Sorry, what'd you say? There we go. Okay. Okay. Period. You have to do the, if it was a t proportional to r, then it would be 5.2. Yeah, 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 exactly. Yeah. Okay, so what we're gonna do here is we're gonna try to figure out, okay, so I'm gonna send you over in groups here and you guys are gonna try to figure this out. So the general idea is the same, it's just that this time Jupiter is 5.2 AUs away from the sun and you need to figure out how long does it take to go around the sun. So it's not going to be, the answer is not 5.2 years. And this is because the relationship is not a one-to-one, it's a t squared to r cubed relationship. So you need to use that relationship to try to figure out what Jupiter's orbital period would be. So remember that Jupiter is 5.2 AUs away from the sun, and use that to figure out the orbital period.
Mr. Hugh, could you add me to the breakout room? Thank you.
it's really helpful having someone here to tell me this. The problem is, what happens is that if I'm muted, no one will say anything. Someone might type it in, but if I'm talking and I'm muted and I'm not reading the chat, I just won't know that I'm muted. So it's really helpful to have someone just tell me that I'm muted. But anyways, okay, so I'm gonna quickly go over this. So we're just trying to figure out what is Jupiter's orbital period. I'm not even okay. See, that stuff like that is really helpful. Okay, there we go. Perfect. I know what I'm doing. Okay, so we need to figure out what Jupiter's orbital period is. And so we're going to use this relationship, t squared related to Jupiter. So basically, Earth's orbital radius. So I'm going to use r subscript e. This r means the total orbital radius. E just means Earth. This is 1 AU. We calibrated our measuring systems to use this. And then the Earth's period of rotation, basically how long it takes to go around the sun. This is just 1 year, right? We just calibrate here. So nice and easy. So basically the ratio of Jupiter's period and the radius compared to Earth's should follow this relationship. So basically Jupiter's radius, I'm gonna call this Rj, over Earth's radius, this the orbital radius, this cube should follow the relationship of Jupiter's orbital period, Tj. I'm trying to call it T subscript J. T means period, how long it takes to go around the sun. J means Jupiter. So I'm gonna follow this relationship right here. So this should be related to this, essentially. Now, Jupiter's orbital radius, as given in the problem, is 5.2. Earth's orbital radius is 1 AU, so I'm just going to put this in here. This cube should be related to Jupiter's orbital period, which we don't know, but that's what we're trying to solve, and Earth's orbital period, which is 1 U. Usually when this turns out, it turns out that Jupiter's orbital period squared should be related to 5.2 cubed. So Jupiter's orbital period squared would be 146. And so when I take the square root of this, Jupiter's orbital period should be 11.86 years. So basically just take the ratio of Jupiter compared to Earth, cube that, and relate that to the period squared. But yeah, so this is gonna be kind of complicated, but we'll try to get some more practice in next week before. Yeah, answer is 11. Yeah, 11 point. Yeah, exactly. Yep. Okay, so that'll be it for today. We're gonna continue this next week, but we're gonna move on to the major, I guess, like assignment for this unit next week. So there's not gonna be much instruction left. So if you have any questions, you should definitely let me know so I can clarify them before we get into instruction. Other than that, I'll see you guys on Monday. So